Hello guys. First I would like to wish you a happy new year. I hope you had great holidays and I hope you're rested now. I am recording this video to talk a little about the neoclassical growth model. Um, we saw this in our macroeconomics 1 class, and one of the things we learned about this model is that this model cannot be fully solved analytically. This means that we cannot fully characterize all the variables in equilibrium in the model just by using pen and paper and algebra and using mathematics. Okay, um, so to fully solve the model, we need to simulate the model in the computer, and that's what we're gonna learn to do today. This is the last slide that we had in class. You should remember this slide. And we saw that the neoclassical growth model is in general equilibrium. The two most important variables, which are consumption and capital, these two variables are represented by these two differential equations. Okay, we see here that the growth rate of consumption, C dot over C, depends on capital and also on the parameters, depreciation rate, time preference, and the other parameters. And that the change of capital over time depends on the level of consumption, on the level of capital, and on the parameters. We used a tool called the phase diagram to understand a little bit more about capital and consumption in the model. And we got to this graph. In this graph, we have capital in the horizontal axis and consumption in the vertical axis. So each point in this graph represents a pair of capital and consumption. We learned that in general equilibrium, the economy will start at a given point. The initial capital is a parameter, but the initial consumption is endogenous, and we need to learn how to determine this. In class, we learned that there's only one initial consumption that satisfies all the general equilibrium and optimality conditions. And so the economy will start at a given point, and then if the initial capital is lower than the steady state capital, consumption and capital will grow over time, right? So capital and consumption is growing over time because we see that this arrow is pointing here up and right. And so the point here in the economy is moving to the right and up. And moving right means that capital is increasing, and moving up means that consumption is increasing. So today we will learn two things. First, we will learn how to simulate the paths of consumption and capital. So think like this. Imagine that we know C0. Do we know how to find the path of the two variables, consumption and capital? We saw in class that we cannot analytically solve this system of differential equations. So if we knew how to solve this, we would know how the level of consumption would be, for example, at a given point in time, if we knew the initial consumption. Okay, but since this is not the case, we cannot find a formula that describes consumption at time t. We only know how consumption changes over time. Since we don't know the formula for consumption at time t, we need to simulate this path. So we will learn how to use a very traditional approximation method to solve for a differential equation. So that's the first thing we're going to learn. If we knew the initial level of consumption, we are able to simulate the paths of consumption and capital. And the second thing that we're going to learn is how actually to determine the initial level of consumption. So this class will be divided in two parts. You can think like this. First, we'll learn how to simulate a path of a variable that is described by a differential equation, which is this case for consumption and capital here. And then in the second part, we will learn how to determine the initial consumption. after we have these two, we have a full characterization of the model, right? Because we will be able to know the values of consumption and capital over time for any time period. And then from these two variables, we can find all the other variables, such as the interest rate, the wage rate, the savings rate, and all the other variables that we want. Right. Let's start the first part of the class now. And we're going to learn how to solve a differential equation in the computer. So let's call our variable x. That's the variable we want to characterize. And this variable is a function of time, t. Time is continuous and starts at 0. But we don't know the function x of t. This means that if we know t, for example, we want to know the value of x at time 10. There's not a formula for finding the value of x. That's why we're going to need to use the computer. So we will need to simulate the variable in the computer. And to simulate x in the computer means that we will compute the value of x for a finite number of time periods. So for example, we can go to the computer, write a code, and then find the values of x at time 0, 0 0.1, 0 0.2, 0 0.3, up until 100, for example. There are two things we need to learn, to know, to use this method. We need to know the value of x at some point in time, just one. In this case, let's assume that we know the value of x at time 0, which is what will happen in the macroeconomic model. And then we need to know the differential equation. So we know how x changes over time for each point in time. This means that we know the derivative of x with respect to time for all time periods. So here is an educational example of this method. The blue curve is the function x, is x as a function of t. Okay, that's the function we would like to know. Let's say that we don't know this function. And we know the value of x at time 0. Okay, so this is represented by this dot here. We have at time 0, we have x 0. So we know the derivative of x with respect to time at time 0. And this derivative says how x changes in time 0 if t increases by an infinitesimal amount. Okay, that's the definition of a derivative. But if we assume that, let's start with a very simple example. So let's assume that if t increases from t equal to 0 to t equal to 1, let's assume that's a small increase in t. If we assume that this is a small increase in t going from 0 to 1, we can approximate the value of x at time 1. And then we can use a very simple intuition, which is the following. The value of x at time 1 will be approximately equal to the initial value, x0, plus the approximate change of x when t goes from 0 to 1. And this approximate change is given by the derivative. Okay? And we call this the x hat of 1, which is the approximation of x at time 1 using the Euler method. So here's an example. Let's say that we apply this formula, and then we find that x hat 1 is this value. And we would not be able to know the real value, but since this is an example, let's say that the real value of x1 is this value. So these two values are not equal exactly. And this is because we are using an approximation. So the difference between these two values are the approximation error, right? The method is not perfect. We are simulating things in the computer, and simulating always involves approximation and numerical errors and computational errors, okay? And there's a graphic intuition for this method, which is let's look at this point here. The derivative of x with respect to time at time 0 is the slope of the blue curve, right? So let's say that the slope is represented by what this red line here is describing. So the method involves using the slope, which is what we know, right? We don't know the value of the, we don't know x, but we know the slope of x at all points in time. So at time 0, the slope is this red curve, and then we move along this curve, you can think like this, up until we get to time 1. And then when we get to time 1, we'll check the vertical axis, and then the value in the vertical axis corresponding to the red curve at time 1 would be this one here. So this is the value that the Euler method predicts for x at time 1. If x were a linear function of time, this approximation would be perfect, okay, right? But it's not linear, so this is what we get. So the Euler method is a linear approximation method. We are going to use the slope, and then we're going to simply use the slope to get an estimate on, or an approximation of x at a given point in time. We will see that we can get this approximation improved. We can get better approximations if we use smaller jumps in the time variable here, right? So here we are using time 0 to get the value of x at time 1. But if we wanted to know the value of x at time 0.00001, very close here, you can see here that the approximation would be good, right? Because the red curve would be very close to the blue curve here. But that's the intuition of the method. And we're going to see in the next slides how to formally to apply this method for smaller time gaps, okay? So let's say we want to know the value of x at time 1, 2, 3, 4, and 5. We can just repeat the same procedure and then find the values. And here's another, I think it's an intuitive case. So here at time 3, the slope of x with respect to time is 0. So the method would estimate that the value of x at time 4 is the same value as x at time 3 because the slope is 0, right? If the function, again, if the function were linear, we would be getting the correct value of the function. And as I said, if we are thinking about smaller gaps between time periods, so t going from 0 to 0.0001, the approximation gets better and better the smaller the time gap. Okay, let's see how to apply this method formally. So again, we know x, x is a function of t. We don't know this function, but we know x of 0, and we know the derivative of x with respect to time for all time periods. And we are using a notation x dot of t, okay? And then using the definition of a derivative, remember that the derivative of x with respect to time is the difference between time of x in two time periods when the difference between the two time periods go to 0, okay? And then it's the difference between the x in the two time periods divided by the length of the time period. And the derivative is this thing when the length of the time period goes to 0. So instead of thinking now that the length of the time period is going to 0, let's think about, we have a very small time period length. Let's say that the length of the time period is this delta, is 0.01. So using the definition of the derivative, which is a limit, we can know this here, that the real derivative of x with respect to time is approximately equal to the expression in the limit, but now we're using a delta that is not going to zero, tending to zero, but is a very small delta. Okay, since this delta is very small, then the right-hand side is approximately equal to the left-hand side. Remember that the left-hand side is the limit when delta goes to zero. So we can use this relationship and make some algebra here, and we can isolate x in time t plus delta, and we get this here. So x at time t plus delta is approximately equal to x at time t plus delta times the derivative. So if you notice, that's the relationship we used in the example before. If you think that delta is equal to 1, so x at time t plus 1 is approximately equal to x at time t plus delta is equal to 1 times the derivative. Okay? So what we are learning here is that if we want to use time gaps between time periods smaller than 1, we need to include here the size of the time gap. Okay? So what we learn here is this. So if we know the value of x at some point in time and we know the derivative of x at this point in time, we can approximate the value of x after a small period of time, delta, using this equation. So for example, let's think about the time gap between being 0.01 and we know x of 0, remember? So we can approximate the value of x at time 0.01 as the value of x at time 0 plus the size of the time gap, 0.01, times the derivative of x at time 0, which is something we know. Okay? And then we can iteratively apply this method. After we know x, the approximate value of x at time 0.01, we can get the approximate value of x at time 0.02 using the previous value that we found. And we do this many times and we can get the path of x. So let's go to an example. We saw this equation in the macroeconomic model. This differential equation describes the rate of growth of population. The population is L, and we saw that the growth rate of population in the model is fixed. It's equal to n, which is a positive parameter. So this means that the population size grows in percentage terms by a fixed proportion all the time. We learned how to solve these differential equations, remember? And the solution is this. So the population size at some time period t is given by this function. We know n, and we just plug t here, and we can know the value of the population size at each point in time that we want. But let's assume that we don't know this, and we would like to use the Euler method to simulate L. Okay, so let's use the Euler method to simulate L from time 0 up until time 1000, and let's choose a gap between time periods equal to 0.01. So we will learn how to compute the approximate values of x at time 0, 0, 0.01, 0.02, 0.03, etc. So remember that we need to use the derivative of L. So if you just put this L in the denominator to the right hand side, we find that L dot is equal to L times n. So we're gonna approximate the value of L for different time periods using these equations. We know the value of L at the first time period, it is 1. And then L at time 0.01 is L at time 0 plus the time, the gap between time periods that we determine, times L0 times n, right? This is the L dot. I cannot select here, I don't know why. Right, this is L dot here, L dot 0. Okay, and then same thing. L in the next period is the approximation that we found for time 0.01 plus the delta and L dot 0.01. Okay, so let's go to MATLAB and simulate this. Right, I have here my MATLAB. Just in case you're curious, I like to put my windows in vertical mode here, so um, you can do the same if you want by dragging, selecting the window and dragging. Right. So we will simulate population size at different points in time. So one thing we need to do to simulate something in the computer is that we need to plug values. So we need to choose a value for n, right? Because we're gonna calculate the numbers, and we need to have numbers to calculate. So let's say that n is 0.01, 1%. So population grows by 1% at each point in time. And there are just two other things that we need to put here. We're gonna calculate for time periods from 0 up until 1000. So let's say big T is 1000, and the delta. Delta is 0.01. So we just put it here. Okay, I'm putting delta with some big D here because it's different from the small delta. So these are the parameters. And let's pre-allocate the variables. So let's create a variable called xl hat, which is this vector will have the value of L at time 0, 0 0.01, 0.02, etc. Before we do this, let's create this time grid. Time grid will be a vector saying the time periods. So the first time period is 0, and delta and t. So let me run this and I will show you what this gives. Okay, I only ran this part here. I can select and then right click and then click here evaluate selection or use F9. And then I can also click here at time grid and then look for open time grid. This will open this table. It's like an Excel sheet. This is showing us this variable time grid. So time grid is a vector that has one column, one row, and a lot of columns. Actually, it has 100,001 columns. The first entry is 0, then 0.01, 0.02, 0.03, etc. If I go to the end of this vector, the last entry is 1000. Okay, so this vector is the time grid. It's a grid with all the time values. Okay, the first time period is 0, the second time period is 0.01. Okay, so we create this value, this variable, using this function in MATLAB. This function in MATLAB, let me give you some examples here. So if I put one, so an example here, if I put 1 colon 10, MATLAB will give me a vector with each entry being 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Here it is. Now, I am using this here. So I want to create a vector that has, let's think, 0, 1, 2, 3 up until 1000. But I don't want the difference between the two numbers to be 1. I want it to be delta. Okay? So that's why I write it like this. So let me show you here. If I want to have from 1 to 10 with a, for example, 1, 1.5, 2, 2.5, 3, 3.5, I use this. The initial value, colon the step size, which this is the name they call it, and the net last value. So if I do this, I get 1, 1.5, 2, 2.5, 3, etc. Okay. I use here CLC to clean the window, just to make it clean. And then L hat, I want it to be a vector. Let's start with a vector that has all entries equal to 0. But then I want it to have the same size as this time grid vector. Okay? So let me create another variable called big N, which is the length of the time grid vector. Okay? Let me run this without selecting the semicolon here because we want to know the result. And you see here that I am defining N equal to the length of the time grid. This variable length, this function length, gives me the size of the object. Okay, so we see here that it is 100,001. So I have this, and I want to create a vector L hat that has one row and big N columns. So I can write zeros, 1, comma, N. Okay, so if I run this, I click F9, I have the variable defined, I can open it, and then I have a column vector that has all entries being equal to 0. So what we're gonna do, we're gonna use a loop to calculate the value of L at time 0, L at time in the second entry will be L at time 0 0.01, L at time 0.02, 0.03, etc. Okay. So the first entry of L hat is 1. Okay, this is L at time 0. We know that this is 1. And now let's start a loop to define the other entries of the vector L hat. So the index will start at 2 because we already have defined the first entry here, and then it will range up until 100,001, which is big N. Let's finish the loop here, close the loop. And then here we just use the Euler method because we are iteratively defining the next values of the vector. So we just use this. So the value, let's take this line here, for example. The value of the vector at a given line is the value in the previous line plus delta times this. Okay, so it is the value in the previous line plus delta times, again, the value in the previous line times n. Right? We have delta here, and we have L hat in the previous period, time period, times n, which is this. Okay? So if I run this, let me now open L hat. I have the population size for some specific points in time, right? Which are described by this time grid vector. So I can plot this. Let me put here some comments. Time grid L simulated using Euler's method. And figure. So let's plot this. Let's plot the time grid. That's the horizontal grid, horizontal axis, and L hat. So here it is. That's L for many time periods. So let me just make the line width bigger. And what is nice here is let's compare this L that we got using the Euler's method with the L that we get analytically, right? Which would be the real curve that we are looking for. So analytical L, let's say, analytical L, we saw the solution to the differential equation, which is this, right? L is equal to e to the power of n times t. I can write it like this. Let's say L analytical is exponential n times time grid. So let's take a look at this. Time grid is a vector. Okay, so we have this vector times n, and n is a constant. It's a real number, right? So in MATLAB, when we multiply a vector by a number, we are getting a new vector that is the previous vector, with each entry being the entry times the real number that we are multiplying. Okay, so we are multiplying n times t here, and then we are taking the exponential. So what we are doing here, we are calculating L at time 0, 0 0.01, 0 0.02, 0 0.03, etc. Right? Just using one line, we can calculate the analytical L for the time periods defined in this time grid vector here. Okay, so I can also plot it here. Okay, and now I want to have the two curves together, so I can open a new figure and write hold on. When I write hold on, it means that I want to put one plot on top of each other. So I already closed the previous figure. I will run this, and then I have the two curves together here. Let me put a grid here. So we have the grid. So for example, I can zoom here the curves just for us to see that they are not exactly equal to each other. Can you see that in the last period here we have a very small difference between the two population sizes? The red one is the one in which we use the Euler method, and the blue one is the analytical, I think, or the opposite. So we can see this by just creating a legend here. The first one is L hat, so we put L hat. The second one is an L analytical. I run. Just a second. Okay, so actually I said the opposite. The L hat is the blue here, and L analytical is the real one is the red one here. So they are not exactly equal, but they are very close to each other. Can you see? So let's see a case in which the approximation is not good. Let's choose a very big delta. So we are using 0.01. Let's put a very large number, 10. And then we're going to run the code again, everything. And the code will make a new figure, which is this one here. So you can see that if we use a very large gap between time periods, 10. So here what we are doing, we are computing the population size at time 0, 10, 20, 30. We don't get a good approximation when we are at time periods, at very advanced time periods, right? Because to get precision, we need to walk in the time grid in a very small steps, because we are approximating. To get a good approximation for L at time 10, we need to know well L at time 9, for example, right? So that's the intuition. So if we want to have very good approximations, we need to walk in the time grid in very small steps. What is the cost of this? Is that if I want to compute the population size for time periods from 0 to 1000, which is the case here, it will take more time if I walk slowly, right? So there's a trade-off. If I want more precision, I will have higher computational cost. Okay? So in general, in computation, in simulations, this trade-off is always present. You need to choose the amount of error tolerance that you want to have, and also thinking about the efficiency and how fast the code will run. Okay? Okay, now let's go to the neoclassical growth model, and we will learn how to simulate this model. In particular, we will learn how to simulate the paths of consumption and capital at several points in time. And to do this, we will use the differential equations that characterize the general equilibrium and the phase diagram that we learned in class also. So just a notation warning. In class, we used, for example, K hat to denote per capita capital in terms of effective units of labor. But just to simplify notation, let's omit the hat. Let's avoid the hat. So all variables here related to the macroeconomic model, we will not use hats, because before we saw that hat also means something for the Euler's method, means the approximate variable. Okay, so first let's start with the assumption that the initial capital is lower than the steady state capital. This is the interesting case in the model, because this is the case in which capital grows, consumption grows, there is capital accumulation, and the model is about growth, right? So let's use the case in which there is growth in the economy, which is the case in which initial capital is lower than the steady state capital. Let's also assume that the production function is a Cobb-Douglas production function, which implies that the per capita production depends only on the per capita capital, and we have that per capita production is A times K to the power of alpha, where A is the TFP parameter and alpha is a parameter that determines the capital share. And also f prime of k will have this specification here, because this is the derivative of this function with respect to capital. So first, let's use what we learned regarding the Euler method and apply it to the neoclassical growth model. So let's say that we have a guess of the initial consumption. So we have a value for the initial consumption. We can use the Euler method and the differential equations to simulate a path of consumption and capital for several time periods. So let's continue with the case in which we define big delta equal to 0.01, which means that we are gonna compute capital, for example, at time 0, time 0.01, 0.02, 0.03, and 0.02, 0.03, and so forth, so on. So we have a guess of initial consumption, and initial capital, let's say here, is also a parameter of the model. So we have K0 and C0. With K0 and C0, we can compute the derivative of capital over time at time 0, just using this differential equation, right? We have K0 and C0, we plug them here in the right hand side, and we get K dot 0, which is this here. We can also get C dot 0. Take a look at this equation, C dot over C. If we multiply both sides of the equality by Ct, we get C dot t as a function of Ct and this right hand side. So if we have, let me go back here, if we have K0, we have C0, and also F prime is the Cobb-Douglas derivative here. So we can compute C dot 0 as C0, which is the guess that we made, times 1 over theta, F prime of K0, okay, and the parameters. So we have K dot 0 and C dot 0. With them, we can now use the Euler's method, which are these two lines here, to get K in time period 0.01. And this is the Euler's method formula. So K at time 0.01 is K in time 0 plus delta times K dot 0. And we do the same thing for consumption. So we get capital and consumption in the second time period that we are simulating. Okay, in the first time period is time 0, and now we have capital and consumption for the second time period, which is time period 0.01. And then we can go to the next iteration. We can calculate K in time in the third time period, which is time period 0.02. To do this, we need to compute the derivative of capital and consumption at the second time period. So we just use the formula again, the differential equations. But now we are gonna use the variables in the second time period. So K dot in time period 0.01 depends on the variables that we calculated in the previous iteration here. So capital in the second time period and consumption in the second time period. We do this also for C dot. And then now, since we have K dot 0.01 and C dot in time 0.01, we can calculate capital in time period 0.02 and consumption in time period 0.02. So we do this a finite number of times, and then we can compute a path of consumption and capital for several time periods. So that's how we use the Euler method to simulate capital and consumption over time. Okay, but we started with the assumption that we are having a given guess for C0. How are we going to actually find the C0 that holds in equilibrium? For this, we're going to use the phase diagram to help us thinking. So this is the phase diagram, and we have the initial capital here. One thing that we know for sure, that we already learned, is that the initial consumption cannot be lower than the one here in the blue curve. So the initial consumption must be between the consumption that is associated to the blue curve here and the initial capital, which we call C0 upper bound. That's the maximum possible initial consumption. We cannot have something higher. That's why we call it EUB, which means upper bound. And then obvious lower bound is 0. So an initial lower bound for consumption is that the initial consumption must be greater than 0. Okay, so the real initial consumption, the true one we want to find, lies somewhere between the upper bound and the lower bounds of consumption. So we want to find this C0, and then after we have this C0, we can use the Euler's method to calculate the true paths of capital and consumption. So we know that C0 is between the upper bound and the lower bound. But where exactly it is? We don't know initially. So we just make a guess of an initial consumption that is between the upper bounds and the lower bound. What is the most natural guess? It is the middle point of the interval. So the average between the upper bound and the lower bound. So let's call it C0 new. That's our new guess for C0. This C0 new is just C0 UB plus C0 low b, LB, divided by 2. Okay, just the average or the midpoint of the interval. After we have this gas, we are going to simulate a path of consumption and capital starting from this point here, C0 and K0. To do this, we just use the Euler method that we just described. So when we do this, since the gas that we made for initial consumption is higher than the true one, we're gonna simulate the paths of consumption and capital, but at some point in time, we're gonna notice that capital will start decreasing. So we're gonna use the following rule. Since capital starts decreasing at some point in time, we know that the gas we made was too high, so we need to make a lower gas for consumption. So we are gonna update the bounds of the interval where the real consumption lies in. Since we know that the gas that we made is too high, we can make this gas now as the new upper bound of the interval. So when we do this, notice that now we don't have this value as the upper bound. Now the new upper bound is here. And then we can do the same procedure again. Let's now make a new gas for consumption, which is now the middle of the new interval, which is here somewhere. Now the new initial consumption is this one here. And we do the same thing again. Let's simulate the paths of capital and consumption using the Euler's method. So we simulate, but now we're gonna see that at some point in time, now consumption will start decreasing. When consumption starts decreasing, we know that the gas that we made for consumption was too low. And then now we can do the opposite. Now this will become the new lower bound for the interval in which real initial consumption lies in. So that's it. We updated the bounds. And then we just do this many times. And then at some point, this algorithm will converge to the real initial consumption. So we can do this many times. And there are two possible rules that say when we will stop. So we can stop making the interval of possible consumption smaller when we get a path in which consumption and capital get very close to the steady state consumption and capital. So let's say that we are doing this procedure and then we guess a value that is very, very close to the C0 here. What will happen is that we're gonna get a path that will converge to C and K in steady state. And at some point in time, we're gonna see that this path, we have a point in this path that is very, very close to the steady state consumption and capital. When we do this, we stop. Okay, that's what we're gonna do in the code. Okay, another possibility that we can use is that we can stop when the upper bound is very close to the lower bound. So when this happens, we say that the interval has collapsed. The upper bound is practically equal to the lower bound. So this would be another rule to use to say when we should stop using this procedure where we are making the upper bound lower or the lower bound higher. And now, before we start writing the code, we will need to write in the code the values for the steady state capital and the steady state consumption. So let's just go quickly here, and we're gonna see that if we are using a Cobb-Douglas production function, we can have a formula for steady state capital and steady state consumption. We saw that a Cobb-Douglas production function implies that we have f of k like this and f prime of k like this. And in steady state, we have that c dot is equal to 0 and k dot is equal to 0. Let's start with the equation c dot equals to 0. if we come back here, we see that if C dot is equal to 0, then this must be equal to 0. Okay, because theta is higher than 0, then this must be equal to 0, the brackets. So if the brackets is equal to 0, then this relationship must hold, that the marginal productivity of capital is equal to delta plus rho plus theta times x. Using the Cobb-Douglas production function here, we can isolate the capital, and we call it K star. So that's the capital that makes consumption growth equal to 0. So this will be the steady state capital. Look that this is a function of A, alpha, delta, rho, theta, x, and alpha here again. So just a function of the parameters. And now the case in which K dot is equal to 0 implies that we can write C as a function of capital. Let's go back here. So if K dot is equal to 0, we can isolate this C here, put here in the left-hand side. So C0 is equal to f of k minus this linear term, which is written here. So if we plug k star here where we have k of t, we have consumption in steady state. So we can also write consumption in steady state just as a function of the parameters. Here we have a, x, and delta, and k star is a function of parameters also. So we are going to use this in the code. Now let's go to MATLAB. Okay, here we are in MATLAB, and the first things we need to do is to choose some value for parameters. So we have economic parameters, and we also have some computational parameters. Let me write some values here. Theta is equal to 3, rho is equal to 0.02, A is equal to 1, alpha is equal to 0.3, n is equal to 0.1, x is equal to this, and delta is 0.05. So in the next macroeconomics classes, in macroeconomics 2 part 2, I will talk in general how we choose parameters value for a model. Okay, so why is theta equal to 3 here, for example? You could ask yourselves. So in my next classes we're going to talk about this. And there are some computational parameters. First one is delta. That's the parameter of the Euler's method. We're going to use 0.01 just like as before. And also, we are going to need a tolerance level. Let's call it tol. Okay, let's go back to the slides here. So remember I said that we will compute the paths of capital and consumption until a point where we get a value of capital and consumption at one point in time in which this capital and consumption are very close to the steady state values of capital and consumption. So we have this notion of very close. So how much very close should be? So this is a tolerance level. The tolerance level that we're going to choose is 0.0001%. In percentage terms, this is equal to 0.01%. So what we will do, we will find a path of capital and consumption such that at some point in time, let's say capital is close to the steady state capital by a margin of error of 0.1%. So that's our tolerance level. Okay, same thing for consumption. Okay, next thing we need to do here is to compute the steady state values of capital and consumption. Note that we already have values for the parameters. That means that we can find the values of capital and consumption in steady state. So we just talked about capital in steady state. Capital in steady state is given by this formula, so we can write it here. Let's write K underline SS, steady state. So we have the numerator being A times alpha. Let's write it like this, A times alpha. And the denominator, which is delta plus rho plus theta times x. And then this fraction is to the power of 1 over 1 minus alpha. We can do it like this. Okay, so if I run this, we have the value of K in steady state, 3.3. Let's also compute consumption in steady state, which is this here. A times K in steady state to the power of alpha, x plus n plus delta times K in steady state. That's it. So I run it, and then we have also consumption steady state is equal to 1.1. Okay, we need a value for the initial capital in the first period. K0 is equal to, let's say that it is 30% of the capital in steady state. Okay, if we choose 90%, it means that the initial capital is close to the steady state capital. If it is 1%, it means that it starts very far. Let's just choose this 0.3 here. Okay. Now initial bounds for consumption. Remember that when we start, we know that consumption is higher than 0 and lower than the upper bound. So let's call here C0 UB, which is the upper bound. How do we find the value of the initial upper bound for consumption? Notice here that the initial value for the upper bound of consumption is associated to the K0 locus when the capital level is the initial capital. So there's a slide here. So when K0 is equal to 0, we have a relationship, K dot 0 is equal to 0. We have a relationship between consumption and capital. So if we put the value of K0 here, this will give us the consumption level that makes K dot 0 equal to 0. So notice here that this is exactly this function that we wrote in the code, but instead of using KSS, we use K0 here. So I can just substitute here and here, and this is the initial value of consumption, possible value. So it is equal to 0.9. Just like the figure, this value is lower than the steady state value, here and here. And also the lower bound is 0, okay, which is this one here. So let's make the first guess of consumption, which is the midpoint between the upper bound and the lower bound. So we sum lower bound plus upper bound and divide by 2. And this is the first guess of consumption that we have. Okay, so notice that in this procedure that we're going to follow, at each iteration, we are going to use one value that we have already calculated of capital and consumption, so K0 and C0, to calculate a new value of capital and consumption. In this first iteration, we will have the new value of capital being capital in time period 0.01, and the new value of consumption as consumption in time period 0.01. Then we're going to go to the next iteration, in which we will calculate a new value of capital using a previous value of capital that we computed before. Okay, so at each iteration, we're going to have a variable called k new and k old, c new and c old. Okay, so in the first iteration, k old will be capital in the initial period, and c old will be consumption initial period. And k new will be capital in period 0.01, and same thing for consumption here. In the next iteration, k old will be now capital in time period 0.01, and consumption old will be consumption in time period 0.01. And capital new will be capital in time period 0.02, and consumption new will be consumption in time period 0.02. So let's call our variables here k old is equal to the initial capital, c old is equal to the initial consumption. Okay, so now we have a guess for C0. Let's see what can happen from now on. If we have a guess for C0, let's say we have this guess. We will use the Euler method to simulate the paths of consumption and capital. And we can have a situation in which capital starts decreasing. So if this happens, we'll tell MATLAB to stop simulating the paths of capital and consumption. The other thing here can happen also is consumption starts decreasing. If this happens, we will tell MATLAB to stop simulating. But if this happens, we will do something different than if this happens. So if this happens, MATLAB will stop simulating the paths, and we will update the upper bound of the interval to be the guess that we made. Okay. But if consumption starts decreasing, we will update the lower bound. Okay, that's two things that can happen. One thing that can happen is that we are simulating this path, and then we get a new value of capital and consumption that is very close to the steady state, capital and consumption. If this happens, we're gonna tell MATLAB two things. First, to stop simulating the paths of consumption and capital, and second, to stop updating the bounds of the interval, because we have already found the solution. Okay, C0. So we will have a variable that says to MATLAB whether to continue simulating the path, and also another variable that tells whether MATLAB should continue updating the bounds for consumption. Okay, so let's call one variable flag update C0. So MATLAB will start simulating, will start updating C0, and we use flag for this. So flag is used by some people who code. It's like a flag. We're telling MATLAB, look MATLAB, continue updating C0. The flag is up. But then if we don't want MATLAB to continue doing this, we put the flag down. But we start with the flag up because we want MATLAB to do it. So we have a flag for MATLAB to update the consumption, the initial consumption, and another flag to simulate the paths of consumption and capital. Okay? And we have the following parts of code, pieces of code now. This should be actually here. So we have this structure for the code. MATLAB will start updating the bounds of consumption, and MATLAB will start simulating the paths. Okay, so one thing about the while loop, if for those who don't know the while loop works similar to a for loop. So what will happen is the following. We are saying to MATLAB, while this variable flag simulate paths is equal to 1, you will do something that will tell you to do here inside this loop, right? But there will be an iteration here in which we will make this variable equal to 0. So when MATLAB finishes this loop, MATLAB will check, look, is this variable still equal to 0, to 1? And then in this case, MATLAB will check, oh, look, it's not 1, it's 0, so I can leave this loop. Okay, so that's how a while loop works in MATLAB. So if we want MATLAB to simulate the paths, how do we do this? We use the Euler's method. So let's go here to the Euler's slides. And to use the Euler method, we need to compute the k dot and the c dot to get the new values of the paths. Okay, so the new value of capital and the new level of consumption. So let's start calculating k dot. So k dot is equal to a times k ode to the power of alpha minus c ode minus x plus n plus delta times k ode. C dot is equal to c ode times 1 over theta times a alpha k ode alpha minus 1 minus delta minus rho minus okay, this is k dot and c dot, and with this we can calculate the new paths of capital and consumption. So k new is equal to k ode plus delta times k dot, and same thing for consumption here. Okay, done. So here we are using the Euler method to calculate a new value for capital and consumption. So the value of capital in the next period and consumption in the next period. So we are inside this flag simulate paths loop. There are 4 things that can happen here. First, if consumption starts decreasing, we will do something. Else, if capital starts decreasing, we will do something else different. Another thing that can happen is that capital and consumption are close to steady state, where we'll write some part of the code here, and then something else can happen that we will talk about this in some minutes. So the condition to check if capital and consumption are close to their steady state values is the following. If so k new minus kss divided by kss, that's the percentage distance between k new and kss, right? So if this is smaller than the tolerance in absolute terms, okay, so if the absolute value of this expression is lower than the tolerance, this means that capital is close to the steady state value. Okay, we want to check if capital and consumption both are close. So I just copy and paste this here, and I change k to C here. Just for security, I will move this to the first check here. Okay. I did a small change here. I moved the if conditions, and first we will check if the new value of capital is close to the steady state, the new value of consumption is close to the steady state. Okay, so if this happens, we want MATLAB to stop simulating the paths. We also want MATLAB to stop updating the consumption, initial value of consumption, because we already found a good approximation to the initial consumption. Okay, if consumption starts decreasing, we don't want MATLAB to stop updating consumption, the initial consumption. Actually, that's what we want MATLAB to do. But we want MATLAB to stop simulating the paths. We already know that this was not the path that we want, so actually we make flag simulate path equal to 0 here. Okay, so if this happens, remember, we are in the case in which consumption starts decreasing. So we are in this case here. If this happens, we want MATLAB to update the lower bound of the interval to be equal to the guess that we made previously for the initial consumption. So lower bound is equal to C0. Okay. If capital starts decreasing, it's the opposite. We want now the upper bound to be equal to the previous guess of the initial consumption that we made. Okay. So, and there's a last thing that can happen, which is if the variables don't converge, if consumption doesn't decrease, and if capital doesn't decrease, that's the last case that can happen, which is we are in a situation like this. We are increasing, we are in a point here, and we are going to another point in which capital is increasing, consumption is increasing, and we are far from the steady state. Okay? We could also be in a point here. We have a point here, and then we simulate another point in the curve. Consumption is increasing, capital is increasing, and we are far from the steady state. So if this happens, we just need to update the values that we call old. Okay, so the old value of capital is what we calculated in the current iteration, and the same thing for consumption. So let's understand this part of the code. Okay, we are in a given iteration in which we calculate the new value of capital and the new value of consumption, and they depend on the old value of capital and old value of consumption that we calculated. When we go to the next iteration and we want to calculate one more value for capital and consumption, the old value of consumption is not C0 anymore here in this example. Now it's C0.01, which we called before C new. So that's why here we are calling C old is equal to C new, because we are relabeling, and what was before called C new, now we call C old. Okay, we are just redefining this variable C old so that it will be used to calculate the C new, and also the same thing for capital. Okay, there's one last thing we need to do that I forgot here. So when we update the bounds of the interval, here and here, we also need to calculate the new consumption, right? So that's a case here. We update the upper bound, and then we get a new guess of consumption, which is the middle interval of the new, the midpoint of the new interval. So let's do it here again. So I can just copy this because that's the same formula. And when I update the upper bound, I calculate the new C0, and same thing for the lower bound here. And another thing that we should change is every time we recompute the initial consumption, we need to redefine the cold variable, right? So we can move these two lines of code to here. Since we are writing the code from scratch, we write some parts of the code and then we need to reallocate some lines of code. That's very normal to happen. Okay, so the code is now ready. So let's go again over the code. This main loop part, which is the most important part. Let's just put some comments here. That's the initial gas of initial consumption. Flag that says to update the bounds for C0. Okay, so main loops. Okay, so MATLAB will calculate the steady state capital, steady state consumption, initial capital, the initial bounds for consumption. Then MATLAB makes the initial gas for initial consumption, and then we turn on the flag for MATLAB to update the intervals, the bounds for the interval of consumption. And then MATLAB enters the main loop, and we define the previous calculated value of capital as the initial capital and the previous calculated value of consumption as the initial consumption. And we are saying to MATLAB, look MATLAB, now we want you to simulate the paths of consumption and capital. So MATLAB enters this while loop, and we use the Euler's method to calculate new values of K and C, okay, capital and consumption. And then we calculate them. So 1, 2, 3, 4 things can happen. First, if the code gets to this line, we will say to MATLAB, look MATLAB, you don't need to keep simulating the paths of consumption and capital, and we don't need to update the values of C0 because we already have found a good approximation for C0. Okay, if we get to this part of the code that says that consumption starts decreasing, we don't change the value of this variable, update C0, because we actually want to update C0. We want to update the bound for the interval of C0, and then we want to update C0. Okay, so just for the code to make some more sense, I will change this line and I will put it somewhere here, okay? Because this will not make any difference, because the code will go back to this to update, and I'm gonna do this just for the code to, for this flag names to make sense, because when we want MATLAB, the code to update the C0, the line of code appears here, okay? So when MATLAB, let's go back. So when MATLAB gets to this part of the code, we don't want MATLAB to keep calculating the new values of consumption and capital, because we're going to be in this situation in which consumption starts decreasing. We don't need to keep walking in this line, you know. We already know that the gas of C0 was too low, so we just need to update the gas. So we say to MATLAB, stop simulating the paths, update the lower bound. So MATLAB will leave this if loop here, and then MATLAB will get to the end of this while loop, and it will check, should I keep simulating the paths? Since we make this equal to 0 here, MATLAB will see that this is not true, so MATLAB will leave this while loop, and MATLAB will arrive to the end of the first while loop, which is this one here, and MATLAB will check, oh, should I update C0? Since we haven't changed the value of flag update C0, which is initially determined to be 1, we didn't change it here, this would still be true. So when MATLAB arrives here, it would say, okay, I should keep doing what I'm supposed to do here, and then MATLAB will update C0, and it will redefine K-ode to be initial capital, and it will redefine C0, C-ode to be the new gas of initial consumption, and then it will start simulating the paths of capital and consumption again using the Euler's method, and then we'll go everything again here. The third option is very similar to when consumption starts decreasing. It happens when capital starts decreasing, so it will do a similar thing. The only difference is now that we will update the upper bound of the interval of consumption, initial consumption, and not the lower bound, which is what happens in this case here. And finally, the final thing that can happen here in this loop is that we still want MATLAB to simulate the paths of capital and consumption, and I already talked about this case. So if I run this code, I click run here, and the code converged because when MATLAB is running something, a symbol appears here, so busy, right? And now since there's nothing showing up here, it means that the code has converged. So for the code to converge, it implies that MATLAB at some point got to this line of code that says that MATLAB doesn't need to simulate the paths and MATLAB doesn't need to update the bounds for consumption. So if we check C0, we got to this C0, and this is a good approximation for the real initial consumption in the model. Okay, we used that algorithm in which I explained graphically, in which we make the upper bound lower or the lower bound higher, and then we get to a consumption that is good, an initial consumption that is a good approximation. So this value is a good approximation. You can take a look at the full value of consumption is this one here. Okay. So when MATLAB got to this part of the code, so what is MATLAB doing? MATLAB found an initial consumption and then simulated a path of consumption and capital, which grow over time. And then, for example, the path of capital got to a point in which the level of capital is very close to the steady state, and we can check it here. This K-new contains the last value of capital in this path that MATLAB calculated. So I can plot the value here, 3.3020, and then I can compare this with the K steady state value, which is 3.3024. The difference between these two variables in percentage terms should be lower than 0.1. Okay. Here MATLAB is only showing the first 4 digits here, but if we calculate the absolute difference between the two variables, which is this part here, it gives something 0.0050 zeros and then a 9. Okay, so this is lower than 0.1%. Same thing for consumption here. That's the last value of consumption in the path that we simulate, and that's the steady state value, which is exactly equal in the first 4 digits here after the comma. Notice here that when we simulate the paths of some variable, let's say capital, we define K-ode, then we define K-new to be the next value of capital in the path, and then we define K-ode as the K-new, and then we compute K-new. Again, a new K-new, okay? So this means that we are not storing the values of the path at each point in time. Okay, so since we want to have the full path of capital, from time 0 up until the time period when it reaches the steady state, let's create a vector that will store this, and then we will simulate the path again one last time um, to store the full path of capital and consumption. Okay, so let's call k path, and initially I will define it as a number. So k path is k0, the initial capital, and c path is c0. But what we will do, we will add one new column to this vector at each iteration. So this is a number, but then it will become a vector with 2 columns, then 3 columns, then 4 columns, etc. Okay, so so then we just need to copy some parts of the code here. So if we copy this, here, if we copy this, we will simulate the path of k and c again. So we will use the others method, and each time we calculate the new value, we add the new value of capital to k path. So we do this like this: k path is k path, comma, k new. So when we do this, we are saying to MATLAB, look, I want to define k path as a vector that all the first entries are the same one as the ones in k path, and then I will add a new column which is k new. So we do this for capital and for consumption. MATLAB doesn't like this. MATLAB says to us, the variable k path appears to change size on every loop iteration. Consider pre-allocating for speed. So MATLAB doesn't like when we are defining a vector that is growing, its size is growing over time, because this is bad for memory in MATLAB. MATLAB gets slow when this happens. But since we are doing this only one time in the code, this is not a big deal, so let's just ignore this. So let me try to run it. Here it is. So we have this k path now, and we have a vector that has 10 we have a vector that has 10,000 columns. Okay, so that's the size of the k, of the path of k, and let's plot it. Let's see if it looks okay. Great, it looks very good, which is an increasing and concave path of capital. Okay, this part here should not be k new, it should be c new. So let me put this right, and then I can try to plot c path here. Okay, and we have here the path for c. So let's try to do now a figure with the paths of capital and consumption and some other variables, interest rates and wage rate, etc. And to do this, we need to have a time grid, right? The time grid should be a vector that, remember the delta is 0.01. So the first time period is 1, the second is 0.01, the third is this, and we should have a vector that has the same number of columns as the path variables, right? Which are 10,560 columns. So we want to have a vector that starts at 0 and it goes in steps of 0.1, and it has 10,560 columns. So the formula for this is something like this. So let me write length of k path time grid, and here it's delta. So if I run this and then I open this variable, it is 0.01, and then it has 10,560 entries here. Okay, that's what we want. So this is just a mathematics simple thing. You can check this, you can do the calculations in your pen and paper, and then you see that this will work. Okay, so I copied some code that I written before to calculate some variables here. So for example, production is given by the Cobb-Douglas production function evaluated at the path of capital. The interest rates in equilibrium are determined by the firm's optimal choices. If you remember our classes, we have this optimality condition for the firm, and we can isolate R as a function of K and delta. We have this. The wage rate we can calculate using this expression in our slides. And the savings rate is consumption divided by production, would be the proportion of production that is consumed. So 1 minus this would be the savings rate. So I also copied some codes here to do some figures. So if I run the code, we get the paths of the 6 variables: capital, consumption, output, savings, interest rates, and wage rate. So we see here that the economy converges to the steady state. So production increases fast in the beginning, in the earlier stages of growth of the economy, and the inputs also increase. So per capita capital increases and reaches a steady state. Consumption increases. In the model, for some parameters, the savings rate can be decreasing, and for other parameters, the savings rate can be increasing. There are also a parameter combination in which the savings rate are fixed. So in this case, we have a decreasing savings rate during the convergence. And since capital increases, the interest rate decreases. And we also have increasing wage rate. Remember, population is increasing, so the wage rate increases forever in this model.